He's allowed me to call him Vincent.
Vicente Garzo.
Thank you very much. Excellent. Really looking forward to the talk.
Okay, thank you very much for the presentation. Well, first of all, let me to rest a bit because I have to run a bit in order to arrive here at 9 o'clock English time. So, well, first of all, I would like to thank the organizer for inviting me to this quite nice meeting. It's really a pleasure to be here and actually, well, the organizer have me the opportunity to present some of my last results. Well, as the title of the talk suggests, today I'm going to talk about some results we have derived using the revised kinetic theory for granular mixtures. I don't know if most of the people here is familiar with this theory. It's a quite sophisticated kinetic theory. I will try to skip some details, mathematical details. And my main intention, my main target is to try to convince you that actually, in spite of this, of the complexity of this theory and things like that, I think that it is still a useful and reliable theory to capture some of the trends observed in real granular flows, not only from a qualitative point of view, but also from a more quantitative point of view. Okay, so I will present some specific results. I will compare them with computer simulations by using what is called direct simulation Monte Carlo method. This is a numerical integration of the Boltzmann-Oreskog equation, and by using molecular dynamic simulation. Okay, and I will apply some of the results for a specific problem, the instabilities and free cooling system. Okay, the line of the talk is something like this. First of all, I will introduce the model. Actually, this is the simple model we can imagine. This smooth has spheres with inelastic collisions. I will build the set of Escog kinetic equations for the mixture. Starting from it, I derive the macroscopic valence equations in an exact way. Recall that, well, the theory goes beyond the Boltzmann limit, goes beyond the low density limit. It applies in principle at moderate densities, although when you perform the theory, there is no any problem with the density. In principle, the theory applies for arbitrary values of the volume fraction. Well, once the valence equation has been derived, then I will apply what is the very familiar method in kinetic theory, what the Chapman-Escos method, to get the Navier-Stokes hydrodynamic equations. Before doing it, I have some troubles with it. Let me to look for my, it's here. It's shorter than the other one, but I think that I am not able to arrive there. Anyway, so I will study first of all, the most simple situation. That means homogeneous state, what is called the homogeneous cooling state. That means as the dissipation are inelastic, the state is homogeneous but cooling. This state will be taken as the local reference state in order to solve the Escog kinetic equations to get, in the first order of the expansion, the Navier-Stokes hydrodynamic, and specifically my main intention is to get all the set of Navier-Stokes transport coefficients and to express them in terms of the parameter space of the problem. It means coefficient of substitution, mass ratio, size ratio, etc. Okay, once these equations, or this expression has been obtained, I will compare these forms with several simulations that is possible for several transport coefficients. And this is the main target, to try to convince you about the goodness of this theory. Then I will apply all these, all the Navier-Stokes hydrodynamics. I will apply then to the instability problem. This is a problem Christine referred yesterday in his talk. She was talking about instabilities in gas-solid systems. I'm going to talk about instabilities in granular mixture at moderate densities. And finally, I will conclude my talk offering, well, some remarks and some possible open problems. Okay, as most of the people present here, I guess, know, well, granular matter, when there is some external energy input, granular matter behaves like a fluid system. I mean, in this condition, which are called rapid flow conditions, the motion of grains is quite similar to the random motion of atoms and molecules in ordinary gases. Well, in that case, since this behavior is quite similar to ordinary fluids, well, in that case, one can use a hydrodynamic-like type of equations to describe this kind of granular flows. However, since there is a distinction between both systems, one of the new ingredients in these systems is the absence of energy conservation. One has to take care in order to extend the ordinary fluid equation to the context of granular matter. So it induces some subtle modification of the usual microscopic balance equation. That means in spite of this similarity, one has to take care about this fact. Okay, essentially, well, one of the main goals of my work is to determine what is the impact of the conditional dissipation of the qualitative form of the transport coefficients. Okay, since in this situation the grains behave like in a similar way as atoms of molecules in ordinary fluids, one can apply the usual kinetic theory tools to understand what is the physics behind the behavior of the systems. In this situation, this is important, since although the density of the system is moderate, is not zero, in spite of this fact, even in this case, the dominant transfer of momentum and energy is through very inelastic collisions, which are well localized in space and time. Okay, this is the most important fact in order to understand what is the physics behind the system. Okay, well, in order to isolate, essentially what I want to capture, what is the effect, what is the impact of collisional dissipation on transport, in order to isolate this effect over other what can be important in other instances, I will consider an idealized microscopic model. Is the simplest model one can imagine. That means is the smooth half spheres with inelastic collisions. Well, this is a simple cartoon showing the dynamic of scattering. Here, for the sake of simplicity, I have considered spheres of the same diameter sigma. Well, in the same way as for ordinary fluids, the collisions are specified in terms of the change of the relative velocity at the point of contact. Actually, there is a change of the magnitude of the normal component of the relative velocity. Normal component means the component along the line joining the two spheres of contact. And so there is a decrease of the magnitude of the normal component. In this decrease is measured through this coefficient, which is a positive constant coefficient. I will call alpha. Okay, some people or many people call it E. I will call alpha. So this is what is called a coefficient of normal restitution. This is smaller than or equal to 1. That means alpha equal to 1. I will recover all the conventional results obtained for ordinary fluids. And so you know that here, if you look at this cartoon, here dashed line refers to the direction of the velocity after the collision. You know that as the dissipation increases, the direction of both velocities before and after collision become more and more parallel, and so the collisions try to align the direction of both velocities. In addition, well, since the system is not reversible in time, the direct and inverse collisions are not equivalent, and this is the scheduling law relating the velocities after and before the collision, pure mechanics, you can derive this relation. Okay? So by using this scattering law, it's relatively simple to see that, well, the total momentum is conserved in each binary collision, but there is a loss of energy in each binary collision event.
As well?
No. I will comment something like that related to this fact. That means the spheres are completely smooth. There is no roundness, and well, only the translational degrees of freedom are affected by inelasticity. I would be happy with this model. I will make some comments about some possible extensions of the model. Okay, in that case, the collisional energy, there is a loss of collisional energy. That means it's a binary collision. The energy is lost, and so the loss of energy is proportional to the factor 1 minus alpha squared. Was alpha equal to 1, I recover elastic collision. Okay, this is probably the most simple model. It is used by many people, especially theoretists. And well, it allows one to go ahead and to perform some explicit calculation, especially for the system I'm interested in granular magnitude. So in spite of this simplicity, at least this is my feeling, this is my opinion, the model still captures many properties associated to granular flows, especially those associated with collision anticipation. As he points, one of the people present in the audience, I don't know your name, sorry, points, actually there are two different possibilities of extending the model. One of them is to assume some kind of roundness in the spheres. And so in that case, well, elasticity, well, in that case, not only the normal component of the relative velocity is affected by inelasticity in collision, but also the tangential component of the relative velocity. Rotational degrees of freedom are involved in all the problem. Another question?
Just a remark, because the length scale of the spheres are not encoded in this energy exchange, but including rotational degrees of freedom would allow you to insert that length scale.
I have not understood very well. You are referring to the length scale? What do you mean?
The size of the sphere.
The size, yeah.
Is not encoded in this collision, is it?
It's also included here, no? Well, it's included in the unit vector sigma. And so this is pure mechanics, and there is no doubt about this scattering rule. Okay? And well, this is a possible extension of the model. Another possibility is to, for instance, to consider spheres completely smooth, but a coefficient of substitution which is not constant, which is velocity dependent. There are some people like Thorsten Poschel and Nikolai Bryantov who have claimed that, I agree with them probably, well, this is a much more realistic model than it, but actually, believe me, the price to be paid is very high. I have tried to do some calculations using this model, and well, it's if we want to keep the same degree of rigor or things like that, well, it is not possible. I think it's my opinion. Okay, but these are the two different possibilities. I will happy with this model, and henceforth I will consider only this model. Okay. However, you know that the real granular systems are essentially characterized by some degrees of polydensity and density and size, and so we are in front of multi-component granular system, and this is the system I am interested in. Well, let's consider a mixture of S species. These are the mechanical parameters of the mixture, masses I, diameters, and there are these are alpha ij, means the coefficient of restitution for each for binary collisions of the species I of the species j. Well, it's very easy to extend the previous scattering law for the direct collision, relating velocities before and after collision. This is the expression. Again, as before, there is a loss of energy, which is also proportional to this factor. Okay, for each binary collision, there is a loss of energy, which is proportional to the 1 minus alpha square ij. Okay, so far everything is pure mechanics, and so the next step is to assume that we have all of the number of constituents is smaller, is not of the number of the Avogadro number. However, even in that case, well, the number of constituents is high enough to adopt a statistical mechanic description. This would be my starting point, although I will be happy not considering the exact n-body distribution function, which obeys the Liouville equation, and I will adopt a kinetic theory point of view. Okay, I will be happy to know this object, this guy, at this kinetic level. All the relevant information of the state of the system is encoded through the knowledge of the one particle distribution function. This quantity gives the average number of particles, in that case of species I, which at instant t are located around the point R and with velocity v. This is the crucial quantity in a kinetic theory description. If I know this quantity, I know everything. In particular, I know the macroscopic properties of the system. This is the properties I am interested here in this talk. Well, in that case, and by it's relatively easy to derive the corresponding kinetic equation for this guy, for Fi, starting from the exact Liouville equation. Actually, this is the last equation of the what is called BBG hierarchy, which comes from the Liouville equation. At this level of description, this equation is still exact. It's the last equation of the hierarchy. Now here I have also assumed that the mixture is not isolated. There is some external constant, external force, for instance, such as gravity. And well, the complex part of this equation appears here on the right-hand side, where it gives the rate of change of Fi due to collisions between different particles of this species. Well, this is the expression of this guy. This is only to show you, I only try to show you that actually it also appears the two-body distribution function. We have a kinetic equation for one-body distribution function in terms of two-body distribution function. Unfortunately, this is not a closed equation for one particle distribution function. And in that case, I will assume a kinetic theory approach. That means I neglect velocity correlations between the particles which are about to collide. It is essential to get a closed equation for the particle distribution function. This is the very well famous molecular cause hypothesis appearing in the Boltzmann equation. In that equation, I am still assuming molecular cause hypothesis. This is crucial. And so if I neglect this velocity correlation among the particles which are about to collide, that means before the collisions, not after the collisions. After the collision, of course, velocities of the particles are correlated. So in that case, assuming this approach, the two particle distribution function factorizes into the product of one particle. But additionally, since, well, the density of the system is finite, I am taking into account the finite size of molecules. There is an increase of the collision frequency of the particles which are about to collide. This per correlation function measure volume exclusion effects, measure the spatial correlations in the system. Okay? And so if I compare this equation with the Boltzmann kinetic equation, there are essentially two new ingredients. That means the presence of this k factor, and additionally, if you recall, the distribution function is delocalized. That means delocalized. Sorry. That means I take into account the finite size of molecules, since I cannot neglect them when I compare with the mean free path of the system. Okay. However, well, so far everything seems to be nice and beautiful, at least for me. But however, there are some claims. There are several in these simulations. One of them carried out by Rodrigo, who is here in front of me. I am a very good friend of him. So, but anyway, this is the point. And so, in these simulations claim about, well, it seems that as the density increases, well, velocity correlations also increase, and it seems that molecular chaos hypothesis start to fail. This is true. But at least for me, this is not an unexpected result, but it is also happens for elastic collisions. That means this is also happens for elastic collision. As the density increases, molecular chaos hypothesis starts to fail. But in spite of this fact, the Enskog equation, it seems to be, well, it yields very good agreement when one considers densities which are beyond the range of values of phi, which we can expect that the equation is good. The good point, at least for the revised Enskog theory, is that it seems that the impact of molecular chaos hypothesis, the failure of molecular chaos hypothesis, the impact on the transport properties, it seems that this is not quite relevant in the sense that, well, so far, well, there are some evidence about the good agreement, about the goodness of the result derived from this equation at the level of macroscopic properties, transport coefficients, and things like that. And so, because it seems that even for moderate densities and finite dissipation, there are good agreement. I mean, I can believe the Enskog prediction. Well, most of the results shown here in my slide regard to simulations for monocomponent gases and even for experiments. And I think that, well, according to this view, I am still happy with this theory, me and other people like Christine. And, well, we go ahead by using this theory, and we think that this is still a useful theory for granular fluids, which for densities which go beyond the Boltzmann limit, beyond the dilute density limit, and also for degrees of dissipation which goes beyond the quasi-elastic. Okay, this is, oh my God, my starting point. And then I go ahead, I will derive macroscopic balance equation, and I will define the hydrodynamic fields as the first few velocity moments of the distribution function. This is the number density of particles I, the mean flow velocity, defined in the same way as the conventional kinetic theory, and this exotic term, which is called granular temperature. Don't try to make some connection with the real temperature, which is based on the second thermodynamic law. For us, simply is a way of measuring the fluctuations of velocity with respect to the mean flow velocity. It's the second velocity moment of the distribution function. Okay? And then, well, by using, well, according to the mathematical structure of the Enskog collision operator, well, it's also to, well, it is possible to derive the balance equations for the densities of these guys, the densities of mass, momentum, and energy. And let me to remark that the macroscopic equation I am going to show you are still exact, since they are obtained from the first hierarchy equation, without considering the Enskog approximation. For particle proposals, I have to assume a kinetic theory approach. But for instance, if you are interested in using this expression when you perform some in this simulation, you can use it. Okay, these are the balance equations for the mixture. And well, if you compare these equations with those obtained for ordinary fluid mixture, the only new ingredient with respect to those equations is the presence of this same term. I have called this term cooling rate. Some people call zeta dissipation rate. It is called, in Christine's talk, it was called gamma. No, gamma, zeta, no. She is my friend, zeta. No, not gamma, not gamma. Well, this guy measures the energy, the total energy lost per unit time. Actually, this is proportional to the total collision frequency in the system. Okay, and this is only the new term. If you compare those equations with those obtained in the conventional case, this is the only new ingredient. Okay, apart from it, we are able to express all the fluxes in cooling rate in terms of the one particle distribution function. This is what I said, these expressions are exact. I only try to show you that actually it's possible to express these fluxes in terms of one or two body distribution function. This is the form of the mass flux, defined in the conventional way. Pressure tensor has a kinetic and collisional contribution. This is the form of the collisional contribution. I repeat, this is still exact. This is two-body distribution function. This is only a method to show you that actually it's possible to write these guys in terms of the distribution function. This is the heat flux. It has collisional and kinetic contribution. And well, actually, this is the exact form. And finally, this is the form for the cooling rate. Okay, of course, this is proportional to this factor. When I assume elastic collision, zeta is equal to 0, and I recover all the expressions obtained for the conventional. Okay, these are the balance equations. And so, as I guess that most of the people present here know, unfortunately, these equations are not a closed set of equations for the high dynamic fields. And so, these equations become a closed set of equations when I am able to express the fluxes and cooling rate as a functionals of the high dynamic fields. These are what is called the constitutive relations, relating fluxes and spatial gradients, and I substitute them into the macroscopic equation, and I finally get the nonlinear hydrodynamic equations for the mixture. Okay, and well, in order to get this description, in order to get these macroscopic equations, I have started from a microscopic description, and the bridge linking both descriptions, microscopic and macroscopic, at the level of kinetic theory is built by the Chapman-Escos method. And I assume that for times longer than the mean free time, and for regions of the system which are far away from the boundaries, the bull region, I assume that the system achieves a high dynamic regime. In the language of kinetic theory, high dynamic regime means a normal solution. This is a special solution. It's a very, very special solution in which all the space and time dependence of the distribution function only occurs through a functional dependence on the high dynamic fields. This is a very special solution because, in principle, there is a big reduction of the number of independent parameters which are needed to characterize the state of the system. Since, in general, I would need the infinite velocity moments of this guy to represent the one particle distribution function, to characterize the state of the system. So there is a big reduction, and this is a very simple solution which are connected with the high dynamic description. Okay, in some cases, this functional dependence can be made local in space and time. For instance, when the strength of the spatial gradients is set by boundary conditions or initial conditions, in the same way as ordinary fluids. And so I assume a small spatial gradient, which are situations which are close to the homogeneous state. And so I can expand the distribution function in powers of the spatial gradient. Epsilon which is a uniformity parameter, which is related to the Nansen number, the ratio of the mean free path and a high dynamic length scale of the system. And so I assume that epsilon is smaller than 1, and I only consider only the first order of the approximation. Note that here I am considering situations in which the set of the strength of the spatial gradient is not set by collisional dissipation. Okay, so there are decoupled. Okay, and so that means for such situations, for instance, this approximation is of zero ordering gradients, but in principle, it applies beyond the quasi-elastic limit. In principle, I would like to get this distribution for any value of alpha, the same way as the first order distribution approximation, and so on. Okay, if you consider different states, for instance, steady states, there are some coupling between collisional dissipation and a spatial gradient, and so as the elasticity increases, you have to go beyond the Navier-Stokes description. Okay, and so I am considering such kind of situation. Okay, let me to make some remarks about some concerns about the possibility of obtaining hydrodynamics by using the Chapman-Escos method, by starting from a microscopic description. Okay, actually, these concerns are related to the fact that there is a new time scale for the granular temperature, the time scale is set by the cooling rate rather than for the spatial gradients. This is an important difference with respect to the ordinary fluids. And so in this new time scale, the variation of temperature is much faster than the usual hydrodynamic scale. And so some hydrodynamic excitation became much smaller than temperature. And the main concern about the fact that, well, as the elasticity increases, that means the time scale over which the temperature change is shortened. It is possible that as the elasticity increases, perhaps there were no time scale separation. And so the temperature, it is possible that it cannot be considered a slope variable in the same meaning as for ordinary fluids. That means this is the case, the temperature do not belong to the hydrodynamic excitation, and so, in other words, there is no hedging to hydrodynamics. This is essential in order to get a normal solution in the context of the Chapman-Escos method. This is a formal point, a conceptual point, but this is quite important. And this is the reason for which some people claim that Navier-Stokes hydrodynamics only apply in the quasi-elastic. Okay? And this is the point. Okay. Here, I will assume the validity of hydrodynamic description, because this is quite difficult to see if actually by analyzing the spectrum of the eigenvalue of the Boltzmann linearity operator. This is, well, from a mathematical point of view, so far, anyone has been able to see if actually there is a time scale separation. And so, the only possibility is to assume, this is one possibility, to assume the validity of hydrodynamic description and compare my results with computer simulation where they have been obtained without paying consideration about the possibility of a hydrodynamic description or not. Okay. Okay. So let me to skip some points in my slide. First of all, I will consider the homogeneous cooling state. This is the most simple situation. It refers to a homogeneous state, isotropic state. This is the form for the set of Escos equation. There is a new actor in this movie. This is the partial temperatures. They are not relevant hydrodynamic level because they don't appear in the hydrodynamic equation, but they are quite important from a microscopic the microscopic description. They measure the mean kinetic energy of each species. I can define the granular temperature, and these guys are associated to partial cooling rates, which are measuring the lack of energy conservation of the partial energy conservation for each species. Let me to only say something. Let's consider, for the sake of simplicity, a binary mixture. And so this is the form for the partial cooling rate for species 1. This is for to illustrate what happens. And well, this is the explicit form of these guys in terms of the Escos collision operator. And so if you consider elastic system, this guy is always 0, but this guy is in general not 0 in general. I mean, there is some transfer of some quantity of energy from one species to the other one. So in general, even for elastic case, are different from 0, except if we consider Maxwellians at the same temperature. This is what happens. This is something behind the equipartition theorem for elastic collision. So there is some what is called here the Tate balance, where the energy transfer between species is balanced by energy conservation for this state. Also, we will call this situation in elastic counterpart it's what I call homogeneous cooling state. And so I assume a normal solution. All the time dependence of the distribution function is encoded or is only given through the temperature T. Okay, this is a very special solution. And so for from a dimensional analysis, I can propose this scale solution where this scale distribution depends on time through this reduced velocity. I have scale velocity with respect to a thermal velocity. Okay? In principle, I don't know the explicit form of this guy, but actually I assume this scale form, which is based on the hydrodynamic description. The main consequence is that if actually the only time dependence is through the global temperature, that means that the temperature ratio must be constant, independent of time. It doesn't mean that the temperature ratio must be equal to 1. This is what happens for elastic collision. Look, if you go to the energy balance for the equation for the energy, this is, I call here gamma is the temperature ratio. The time dependent of this guy is the difference between both partial cooling rates, and in the long time limit, if gamma is a constant, means both cooling rates are equal. Okay? For elastic collisions, both cooling rates are 0, equipartition theorem for classical statistical mechanics. But however, if the collisions are inelastic, in general, the temperature ratio is different from 1. Okay? However, the problem is not, the solution of the problem is not exactly known, and so for practical purposes, one assume an expansion for the distribution function in some orthogonal polynomials, such as Laguerre or Sonin polynomials, and the theoretical results I am going to present have been obtained by considering the leading term in this Sonin expansion. Okay, let me now to show you some, to illustrate the goodness of the theoretical predictions, the comparison with Monte Carlo and MD simulation. This is, first of all, for the time evolution of the temperature ratio. This is only to see if actually the simulations support the fact that after a few collision times, the temperature ratio reaches a plateau, reaches a constant value, which can be equal to 1 or not. This is the case for two different systems, the elastic system. The dashed line referred to the theoretical prediction, and you know that after a few collision times, the temperature ratio gets a constant value, and well, the line, well, means the plateau agrees very well with the theoretical prediction. Well, this is one of the comparison. Then, well, this comparison is for checking the accuracy of the Sonin polynomial approach, and you know that, well, this is for the temperature ratio. As a function, I have here in most of the graphs, I have assumed a common value for the coefficient of substitution. It's a binary mixture. There are 3 different values of alpha for 3 different types of collision. I have assumed for the sake of simplicity the same value of alpha. Know that it's quite apparent that there is an excellent agreement between theory and computer simulation. This is for Monte Carlo simulations. Monte Carlo simulations means that the method is still assumed molecular chaos hypothesis. I am checking the assumption on the validity or not of hydrodynamic description and the accuracy of the Sonin polynomial approach. This is a much more stringent test. This is versus MD simulations. This is also for the temperature ratio. MD simulation also support the validity of hydrodynamic description, but in some cases, the accuracy of the, there is some discrepancy between the theoretical predictions obtained from Sonin polynomial approach and MD data, especially for this value of the solid volume fraction and for the high dissipation value. Okay, this is possible. There are a possible source of discrepancy is due to the approach method used to get the temperature ratio, and other possibility is that actually molecular chaos hypotheses start to fail. But I will show you later on some graphs in different problems where this is not the case. Okay, but in any case, well, after this study, well, there are many and different studies. One of them from real experiments by Ricky. This is a relatively very famous paper, so many people refer to it, where all the results confirm this new feature in granular mixture. Sorry. There is no doubt about the existence of this failure. Okay, so the next step is to assess what is the impact, what is the effect of this non-equipartition on transport coefficients. I am going to consider inhomogeneous situation. For time results, in principle, I had 40 minutes. Ricky say, okay, don't worry, Vicente, you have an hour. But actually, it's incredible. I have to speak many of the slides because in principle, the talk will be prepared for 40 minutes only. Okay, let me to essentially to say what is the main motivation. This is our previous studies. I have chosen several very well-known papers. Most of them are limited to the quasi-elastic limit, and so it is plainly justified that they assume energetic partition. And so our main motivation is to go beyond this description to determine.
You have till 10 o'clock, so you do have some time left.
10 o'clock is.
Yeah.
Yeah, I know.
Okay. All right.
I know. Thank you. Okay, and so the main motivation is to determine all the transport coefficients of the mixture, in principle taking into account the effects of temperature differences, and in principle there is no limitation of the degree of dissipation. This is our main motivation, and this is our goal. Okay, this is this is a very huge problem, believe me. So Christine, Jim Duffy, and myself, worked a lot to get them. Let me to briefly summarize some of the results. Let's consider a binary mixture for the sake of simplicity. And these are the constitutive forms for the fluxes. We have 8 transport coefficients are in red. The diffusion coefficients, thermal diffusion coefficients, shear viscosity, bulk viscosity, 2D full coefficients, and thermoconductivity coefficient. Well, our idea is to get these objects in terms of the parameter space of the problem, and reduce unit mass ratio, diameter ratio, mole fraction, solid volume fraction, and 3 different coefficients of diffusion. Unfortunately, all these transport coefficients are given in terms of a set of coupled linear integral equations, and this is a very complex mathematical problem, at least for me, sorry. And so we can resort to some Sonin polynomial approximation, and most of the cases only leading terms are usually considered. And so to test the accuracy of these predictions, we will compare in the next slides in some cases with DSMC simulations, Monte Carlo simulation. Recall that Monte Carlo simulation still assume molecular Gauss hypothesis. Well, first of all, since the results are very huge, well, it's important to see if actually all the limited cases are recovered. That means mechanically equivalent particles. Know that the calculations are made in D dimensions for spheres and disks, and so we recover everything. And so we recover mechanically equivalent particles case, binary mixture at low density, and a relatively old paper for elastic half spheres by using the revised Esca theory. And in some cases, I will use for the zero order distribution the most simple approximation, the Maxwellian form. I will use the Carnahan-Stalin form for the percolation function. But this is for the shear viscosity coefficient. Well, again, for different systems, eta star means is eta reduced with respect to a certain reference viscosity. And well, I think that again it's quite apparent that the agreement is excellent, even for string values of dissipation, 0.7 for instance, is not a line. So agreement is quite good. Another case is for the packed particle problem, for the tracer diffusion coefficient. That means in that case, well, we can measure in simulations this coefficient by measuring the mean square position of impurity, the very well-known Einstein relation for the mean square displacement. But here, even in this case, we have been able to consider the next Sonin correction. We have considered 2 Sonin polynomial approximation, and in some cases, for very extreme cases, the Sonin correction improves the prediction given by the first Sonin ones. Look, this is a very mass disparate case, and so in that case, it's very well. It is very well. It is known in the case of for elastic collision that the convergence of the Sonin polynomial approximation is relatively poor when one considers disparate values of masses or sizes or things like that. So in that case, this is quite evident that again, by improving the approximation, there is a very good agreement. In some cases, for instance, something like that, when the mass of the top particle, the traction particle, is bigger than the, no, it's bigger than the particle of the excess gas, well, practically bosoning approximations tend to collapse each other, but in other cases, such as in the graph here, well, again, the second Sonin polynomial approach improves the result. Okay, so I have 10 minutes only to explain a possible application of all these results. I think that I have tried at least to convince you about the goodness of the kinetic or the S-clock prediction by using Sonin polynomial approaches and things like that, and then they compare very well with computer simulation. And then I'm going to present some preliminary results regarding instabilities in fully cooling granular barrier mixtures. I mean, this is a very well-known problem, and so you know that in contrast to ordinary fluids, a granular system which is driven, which is free cooling, it appears in a spontaneous way instabilities in the system. There is appearing work of Isaac Gorhich and Zanetti, where they were able, explain in his letter in a very intuitive way, what is the reason for which the system develops such kind of instabilities. Essentially, this is it is related to the motion, to the migration of particles from dilute to dense parts of the system due to internal pressure gradients appearing in the system due to the elasticity of collisions. These are very quite intuitive argument. Okay, so actually what I want to see if actually the kinetic theory is also able to predict not only from a qualitative point of view, but also for a more quantitative point of view, what is the onset of instability. Essentially, I will focus on the critical value of the length of the system beyond which the system develops instabilities. The general trends, well, what they were explained by Christine yesterday. Principal instabilities are more likely in larger domains, and so if you want to suppress such instability, you have to consider small enough systems. Another trend is the onset of instability is related to the formation of velocity vortices rather than particle clusters. And additionally, for us, this is a very, very good problem to assess Navier-Stokes hydrodynamic based on kinetic theory results. This is a very, very good benchmark to assess the reliability of the system. Okay, and so for given values of mechanical parameters of the system, I want to see if actually what is the value of the critical system length which separates stable from unstable. Okay, let me to skip some details. Well, it is very well known that the homogeneous cooling state is unstable with respect to long enough wavelength perturbation, and so this is the form of the homogeneous cooling state solution. These are the four I have chosen. These fields, the mole fraction, the total density. This is for a Van Herre mixture for the sake of simplicity. This is the granular temperature. The subscript H means homogeneous case, and this is, well, the only new feature with respect to elastic collisions. The system is cooling, and this is the time dependence of the temperature. It is very well known that this state is unstable, and the idea is to linearize the Navier-Stokes equation with respect to the homogeneous solution, and I assume that the fields, well, I write the fields as there are values in the reference homogeneous state plus a small perturbation, and I substitute these ansatz into the hydrodynamic equation, and I get nonlinear differential equation for the perturbation. I am going only consider only linear terms in this perturbation. And look, I have written here more explicitly the equation for the velocity field, because hopefully this is the couple, at least one of the modes, it is the couple from the remaining modes appearing in the system. Here, again, this is the pressure obtained by, from the equation of state, and the shear viscosity and the bulk density. Okay, this is only a matter to linearize about the base state. The only point, this is a tricky, so all the coefficients occurring in the equations are constant, but they are time dependent. So it's only a matter to rescale time in terms of total is a measure of the total number of collisions in the system and to reduce the space in terms of the mean free path. And so in that case, it is possible to convert the set of coupled linear equations with constant coefficient. I take Fourier transform in dimensional variables. Let me only to show you what happens for the transversal component, which is the couple for the other modes, and this verifies this very simple equation, and this is the corresponding critical wave number for this mode, and for values of k smaller than this mode, the shear mode grows exponentially. This is the critical value of k for the mode, the shear transversal mode. The remaining 4 longitudinal modes, well, they obey a couple, and they add the eigenvalues of 4 times 4 matrix. Well, these are the solution of a quartic equation. Okay, there is a competition between both wave numbers, both critical wave numbers. We have explicit for these wave numbers, and since the system there are periodic boundary conditions, that means that the smallest value of k is 2 pi over L, and so we can get the critical value of L in some reduced units. I don't remember the scale of, I think it's possible the sum of the diameters over 2 is the maximum value of both critical wave numbers value. Okay. Well, what happens in most of the studies we have carried out, actually also the linear stability analysis shows, and also the computer simulations show that in general the system is stable to velocity vortices, but is linearly stable to particle clusters. And so these are some comparisons against computer simulation. First of all, for the monocomponent granular fluids, these are some in-V simulations carried out by Christine's group. And so, well, look, and again here, here is a comparison. Well, it shows the value of LZ versus solid volume fraction for 2 values of coefficient of substitution. Of course, very well, relatively strong values of collisional dissipation. I think that you see that we observe that the agreement is excellent. This is the theoretical result were derived by myself by using a linear stability analysis, by using the Ansgar expression for the transport coefficients. This is another type of graph. Now, well, comparing this guy versus the E is the coefficient of substitution, is my alpha. And so for 2 values of phi, these are for moderate densities and for relatively high densities, and even in that case, the agreement is quite good. However, even in some situations for very high dissipative systems, for very dilute systems, it seems that the theoretical predictions start to fail. But this is not a problem of the Ansgar kinetic theory. It's only a problem of the approximation method used to get the critical length scale. And so we were able to derive, we called a modified Sonnino approximation. The idea essentially is to take as a weight function not a Maxwellian distribution, but the homogeneous Kunig state distribution. The main consequence of this fact is that we have to define a new modified Sonnino polynomials. In that case, we have to construct the scalar product and whatever. But the good point, you see, this is a very good graph showing, look, this is for the standard theory, both lines, and you know that the standard theory predicts that clusters appear before than vortices, and this is not what happens in MD simulations. Our modified theory agree very well with MD simulations. And look now finally for binary granular systems. These are quite preliminary results and published results. And this is for a binary mixture. That means we are now considering a much more complex system. First of all, against mass ratio, even for values 0.7. Well, this is true that as the mass ratio increases for relatively quite disparate values of the mass ratio, around 7 or 10, there is some discrepancies at a quantitative point of view. These discrepancies are of the order of less than 10%. And I would like to improve these theoretical predictions. My plan is to improve these theoretical predictions by considering the next Turing correction, because I am quite sure that the theory will be able to capture this dependence. But know that, well, at least what is important, the theory agree with the simulation data in the sense that as the mass ratio increases for high dissipation, all the data trying to collapse, and so it seems that they are independent of the coefficient of restitution. That means the theory also agrees with this fact. More graphs versus concentration. I think the agreement is quite good. Versus, this is for the size ratio, is perfect. And well, this is a graph Peter sent past weekend. Is for this smaller solid volume fraction, and it seems that actually the agreement is improved. That means it seems that in that case, the leading Turing approximation is enough. Let me to conclude 1 or 2 minutes. Uno, only one? 1 or 2 is important. 2. Okay, no question. Everything is clear. So anyway, these are the main conclusions. It's a joke. They are the main conclusions. So look at them. Essentially, the message to take at home, at least from my point of view, is to see if actually, this quite exotic, sophisticated, complex kinetic theory, I think that it's able to reproduce some object frames observed in some problem, in some specific problem. This stability problem is one of the problem for which actually the theory presents a very good agreement, and this is a quite stringent test for the result. In my opinion, some open problems, of course, to extend the results to inelastic row spheres. I am not quite sure if actually I will be able to do it. I have only made contact with such kind of systems in the homogeneous case for a Vernari mixture. The calculations are, believe me, are quite complex. The other possible project is related to the fact that, well, we have neglected the influence of the interstitial fluid on grains, and what we plan to extend all this stuff to the case of suspensions, based on one paper we have recently published regarding to monodispersed gas solid flows. And actually, one of the open problems really is to try to understand what happens behind problems like simple shear problems which are in a steady state where there is some coupling between dissipation and spatial gradient, and where for such kind of problems the Navier-Stokes equation fail, only applies for quasi-elastic limits. And let me to finish to remark, this is the most important slide in my talk, to help, that means to acknowledge some people who has helped me in many different stages. In my university, Jose Maria Montaneo, who has carried out many of the computer simulation regarding Monte Carlo simulations, Francisco Vega Reyes, who is here. Pay attention to his talk. It's a very good talk about segregation. Some external collaborations with Professor Jim Duffy, which actually was my mentor in this issue. He introduced me in this issue. And more recent collaboration with Christine Renia and Peter Mitrano of the University of Colorado. Thank you very much for your attention.
Okay, thank you very, very much for that, Vicente. We've got some questions, lots of questions. Michelle.
I'm always impressed by the success of the theory that you put together. My own engineering experience is that when particles collide with realistic spheres, surface forces take over when the relative velocity is low. And as a result, the coefficient of restitution is for all intents and purposes, 0 when the velocity is low.
Yeah.
So to what extent will that affect all the theoretical predictions that the restitution dramatically collapses when surface forces take over, which is really what is observed in all the impact experiments we've done and so forth.
Actually, well, you know that, well, I agree with you. If actually we want to approach to reality, of course, the price to be paid, if we want to keep our rigor by obtaining the result, let us to move step by step. Because, well, it's a very simple model, but I think that we can still believe. Okay.
Okay, one more quick question. Yes.
We have seen that the transfer coefficients for inelastic spheres for mixers, it depends very much on the temperature ratio. So would you expect that theories that do not take into account this effect would be in agreement with experiments?
Sorry, Fran, I don't understand you. You are referring to
Do you think that
you are talking about the temperature ratio?
yeah, do you think
One of the graphs?
an issue in order to compare to more realistic situations?
Yeah. Yeah. Well, you said that you should try to make some comparison by using our theoretical result with another kind of data, experimental data. This is what you propose, more or less. Or you propose to refine our theory?
I'm just asking if neglecting the temperature ratio different from 1 is
no, I understand.
or not,
Okay.
in order to compare with experiments or experimental situations.
Yeah, actually, I have not shown any plot where I compare the theoretical predictions by assuming a equipartition theorem and when the temperature ratio is different from 1. And actually, the impact of energy non-equipartition is quite important on the transport coefficient. And so I guess,
Situations.
I guess that it would be the case.
So I think it's time to move on now. So take your discussion.
Thanks,
break.
thank you
Maybe
very
later on.